The land of mathematics is an exotic and puzzling place. A strange language is spoken there, with talk of homeomorphisms, differentiable manifolds, and transfinite numbers. But also to be found there are magnificent landscapes, spellbinding ideas, and occasionally, even useful things. So let's take a whirlwind tour of the land of math. You just need a guide, that's me, and a functioning brain, that's you. We're not really going to do any math, just take a look at the countryside. Today, our little outing begins not far from home, in a setting which is so commonplace that it appears to discourage using one's brain from the very outset. And yet, a mysterious phenomenon is unfolding before our very eyes. A phenomenon which defies common sense and sets the head spinning. Look! Here, here, and here, and again here. Do you see the problem? Let's choose 100 or so items at random. 1 kilo of pure beef ravioli with 5 vegetables, €3.24. 4 rolls of double thickness toilet paper, €1.99. 6 sachets of Alpine fresh washing powder, €12.15, etc., etc. Each of our 100 items bears a price tag in euros, the first figure of which we are going to note down. That's it. We now have a random collection of figures from 1 to 9. Random, really? Let's have a closer look at this harvest. Why are there not as many 9s as there are 1s? Chance would appear to favor small figures over large ones. To be sure of our discovery, we could start again at 0 and choose more items. But nothing changes. The more detergent and cellophane-wrapped cheese we accumulate, the more the distribution of the first figures appears like this. Strange things are happening in our supermarket. And in all others come to that, whether the prices be in euros, yuan, dollars, or rubles. Where does this strange phenomenon come from? Why do supermarkets seem to prefer small figures? To find out, here we are in French Polynesia. French Polynesia, with its dreamlike beaches, immaculate sand, and above all, its 118 islands, of which the surface areas range between 1,045 square kilometers for Tahiti to 0.04 for Maritiri. Let's try our previous operation using the surface areas of Polynesian islands. I take the first figure, put them in order, and find the same distribution as before. There would seem to be a vast conspiracy in operation between supermarket managers and geographers. And it doesn't end there. Whether you take the population of large cities, the turnover of stock market companies, the length of European rivers, or even the distance between stars in our galaxy, the same pattern reappears everywhere, whether we're talking in square kilometers, millions of dollars, centimeters, or number of inhabitants. What's going on? Could our world be a Matrix-style mock-up? Has a bug sneaked into the code? Let's stand back a little and take a look at 2 neighboring planets, the planet Sum and the planet Product. From a distance, they look very much alike, but the inhabitants of these 2 heavenly bodies don't see the world in the same way. Those of the planet Sum see it in terms of addition. Let's present them a sample of life on Earth, made up of a gorilla, a chimpanzee, and an ant. In order to classify them, they measure them. The ant measures 1 centimeter, the chimpanzee 70 centimeters, and the gorilla 1.60 meters. The difference in size between the chimpanzee and the gorilla is greater than that between the chimpanzee and the ant. Consequently, they tend to group the chimpanzee and the ant together, leaving the gorilla to one side. Logical, but a bit strange, no? The inhabitants of the planet Product view the world in terms of multiplication. They also measure, but differently. From their point of view, the gorilla is 2.2 times bigger than the chimpanzee, which is 70 times bigger than the ant. For them, it is clearly the gorilla and the chimpanzee which belong to the same family. And we can't help but be somewhat in agreement with them. It would appear to be that, in certain cases, the logic of addition is not the right one. This is why VU meters, which measure volume of sound, the Richter scale, which indicates the magnitude of earthquakes, and even musical staves, all use multiplicative graduation. So there are two totally distinct ways of measuring the world, between which it seems we have to choose. It's at this point in our journey that a quick dive into the depths of time is in order. Here we are in 1614, which is the precise moment when the Scottish astronomer and mathematician John Napier published his Mirifici Logarithmorum Canonis Descriptio, in which he established the correspondence between the world of multiplication and that of addition. It's a bit of a boring read, but the idea behind it is simple. To each number, you associate another number, which is called its logarithm. The logarithm of 100 is 2, because 100 equals 10 to the power of 2. That of 1,000 is 3, because 1,000 equals 10 to the power of 3. That of 98.456 is 4.99324, because 98.456 equals 10 to the power of 4.99324. Logarithm tables simplify the multiplication of large numbers by turning them into additions. To multiply two numbers together, you simply need to add their logarithms. Between the beginning of the 17th century and the invention of the computer in the middle of the 20th, logarithm tables enabled a vast acceleration in scientific calculations. So at this stage, you could have the impression that we've completely forgotten our problem back at the supermarket, but you'd be wrong. In 1881, another astronomer, Simon Newcomb, noticed that the first pages of logarithm tables, those which contained figures beginning with the number 1, were more worn than the others. From this, he came up with a formula, which gave the probability of a number, n, being the first number of any figure, a formula which provided exactly the same strange distribution as we have in our supermarket, and which interested precisely no one. It was only in 1938 that Frank Benford rediscovered the law which now bears his name, and tried it out on numerous collections of figures. He, for one, thereby managed to grab the attention of his contemporaries. But let's come back to our present-day supermarket. Does the phenomenon still seem quite so mysterious to us? Look, between the packet of pasta at €1 and the packet of biscuits at €2, the price has doubled. While between this cheese at €9 and this bottle at 10, the price has only gone up 11%. To the multiplicative eye, the interval between 9 and 10 is smaller than the interval between 1 and 2. In reality, it isn't the way in which the numbers are separated out which is strange. It's that the scale which we're using to analyze them isn't the right one. If we change from an additive scale to a multiplicative scale, we discover with astonishment that the numbers are evenly distributed. The mystery of the supermarket was no such thing. We simply weren't using the right scale when considering the question. However, not every series of numbers obeys Benford's law. The height of human adults, measured in centimeters, for example, almost invariably begins with 1. For the law to apply, the series needs to cover several orders of magnitude. Taxation authorities use Benford's law to detect tax fraud. If the figures in your declaration don't abide by it, then they're quite possibly the product of your imagination. Figures invented by the human brain know no law. That's how you recognize them.